Hello everyone. So I am back with my last topic that has been assigned to me, and I am going to talk about analysis of variance, which is a very powerful technique, and I'll try to introduce you the philosophy behind analysis of variance. I will not deal much detail about the mathematical formulas and all because they are readily available in standard textbooks, as well as these days softwares are there to do the real nitty-gritty calculations. But I focus what is it, what is the philosophy when it is used, and how do you interpret the results, and so on and so forth. Okay, by this time you must be knowing about the statistical tests of significance, when they are used, what do they do, what do they give, and how to interpret. But to give a quick recap, I'll just tell you the statistical tests are performed when we want to compare two estimates of a parameter. The parameter is same, it could be a mean, it could be a proportion, and to determine whether the difference between them is statistically significant. And this process involves calculating a critical ratio, a ratio that helps to make a decision. And the observed critical ratio is compared with a theoretical statistical quantity which is readily available in standard books, or you can derive through mathematical calculations. And by comparing the observed ratio with the theoretical, what can happen in the idealistic scenario, and comparison helps you to take a decision about the difference, whether it is statistically significant or not. Just to continue on that, the critical ratio could be generally a generic format for this ratio. What we are talking about is a parameter in general, a parameter in the numerator divided by the standard error of the parameter. So if you are comparing two proportions, the standard Z-test is the nothing but the difference between the two proportions divided by the standard error of the difference. So this is what we call the Z-test, and what Z you calculate from your data, then you compare it with the classical theoretical distribution based Z value, and then you use, depending on whether your Z is more than the tabulated value or less, we will take a call or decision about the significance. Let us now talk about a more detailed and a specific scenario. Suppose you want to compare the means of a quantitative variable in two samples. It could be male, female, it could be say rural, urban, it could be a particular place versus another place, and so on and so forth. So in such a scenario, when we want to compare the average or mean of two groups, parameter is one, that is mean, but you have two samples, and we use a test called Ttest, or more specifically student's Ttest. Here student does not mean the academic sense. A student, a person called William Gossett, used to write because of certain personal reasons, because of his employment constraints. So he used to write with a pseudo name called student. So that's how it is called student's Ttest. And for this test, what we require is we have to have two assumptions met. One, the quantitative variable follows a normal distribution, which is fairly straightforward and most often not an issue if you have a large sample size and the variable is reasonably follows, or what I would say, it's not extreme variations are not there. So it tends to behave like a normal distribution. But what is more important is the both groups that you are comparing should have similar variation. It should not be like that one group has the variance or standard deviation is very small compared to another group. Then you have to have some other modified version of the test, or some modification is required. But standard Ttest requires two assumptions. One, the quantitative variable that follows that is being tested or assessed for significance it follows a normal distribution, and both the groups, the variable that you are considering in both groups should have similar variation. Now, what happens if you have more than two groups? Two groups, fine, you have a test called students Ttest, then you arrive at and get a ratio and then compare, take a decision type of things. But when you have more than two groups, and let's see, suppose you have 6 groups, say non-smokers, passive smokers, non-inhaling smokers, light smokers, moderate smokers, and heavy smokers. There are 6 groups, and you want to study whether smoking has any effect on pulmonary health, the lung function. So, a chest physician measured forced mid-expiratory flow, FEF, that tells the lung capacity, the vital capacity, how the lung is functioning, and these values in some number of subjects of these 6 groups. And the idea is to see whether all these 6 groups have similar FEF or not. So, the non-smokers, 200 persons were studied, and the mean FEF was 3.78 liters, and standard deviation was 0.79, and passive, there were 2 people, 200 persons, 3.3 was the average, and 0.77 is the standard deviation, and like that you have the 6 groups, the last being heavy smokers. You have 200 people with an average FEF of 2.59 with a standard deviation of 0.82. See, whenever you look into a data, just don't look at as numbers. Just try to scan what is happening. By mere look, you can see 3.78, 3.3, 3.22, 3.2, 2.7, 2.6. The average is slowly, decreasing. So it gives you a feeling, the gut feeling that yes, as the smoking severity increases, the average FEF is coming down. Now, but this perception, this observation, what you have seen, is it how statistically, is it significant or not, is the question which the analysis further helps us. And by the way, this data is from White JR and Herman FF. It is published in New England Journal in 1980. But this example with more details has been discussed by a very good author, Bernard Rosner, from Harvard School of Medicine. Fundamentals of Biostatistics is the book. So you can see for more. I am using the same example to give you the explanation about the philosophy of this analysis of variance. Now, coming back to the question, how to go about this data? That's the question. You have 6 quantitative parameter of 6 group measured, and equal some numbers are there. So we have a comparison of 6 means at hand. We know that Ttest can be used to compare 2 means at a time. But 6 groups, if you want to do pairwise comparison, you have 15 combinations. So at least 15 Ttest should be performed to arrive at any conclusion. So it looks simple, but it has limitations. While this approach, as I said, seems to be alright, but it has problems because it provides a piecemeal approach. It's not a comprehensive analysis, and more importantly, people don't realize the more tests you perform, the more probability of finding a significant result. So this is the sort of limitations for thinking of a piecemeal approach or pairwise analysis. Before I get into the explanation of an analysis of variance, we can't help to avoid some notations which are very straightforward. These are at best, I can say, +2 level mathematics, which all of you should be comfortable. So let me introduce. Suppose you have, instead of 6 groups in our example, let's talk in generic terms. We have k groups with ni observations. N observations in the ith group is ni. If it is the first group, you can say n1. If it is the 6th group, you can say n6. So Ni observations in the ith group, and now come back to our parameter, a quantitative variable, which we say the dependent variable, the outcome variable is y. Its value on the ith individual in the jth group. Sorry, the other way. It should be the jth observation in the ith group. So if we call that Yij as the value of, in our example, FEF, in the, if you say Y14, then we say it is the fourth observation in the first group, Y14. It denotes the fourth observation in the first group. Then we assume, now this is the, here the question of the philosophy to understand. You need to just imagine that's a particular model, whether it holds or not. Suppose I say an individual's FEF or an outcome parameter, it depends on a constant common for all groups, some effect which is common for all groups, irrespective of the group. Certain value will be there for everybody, which we call mu, and alpha I, it is a constant for the specific group. That is this is for ith group alpha I. I mean, if alpha 1, that is the difference between the common constant common for all groups plus some individual group effect plus Eij, that is some error term which we presume is normally distributed with mean 0 and variance sigma square. So if you understand this model, further we can simply work out and come out with how an analysis variance can be performed and what it leads to type of things. So this model is what is called or referred to as one-way analysis of variance or one-way ANOVA. So ANOVA is a technique with which the means of a number of groups can be compared, but the parameter is same. You can't compare height with weight or weight with blood pressure or something. We can compare height of males versus height of females, height of rural versus height of urban, height of educated versus uneducated type of things. So the parameter is one. So, but the parameter estimates come from different groups which can be compared by a technique called ANOVA. As in the Ttest, here also we have some assumptions to perform the ANOVA, and they are similar. Each group follows a normal distribution. The parameter that we are considering is a quantitative one, and it follows a normal distribution in each group, number one. Number two, the variance in each of this parameter in each group is similar. So the same, instead of groups there, in Ttest we say two groups there. Here, because it can be more than two, we will say all groups. So coming back to ANOVA model, the model is Yij, that is the outcome, the quantitative outcome of jth individual in the ith group is a common mean for all groups taken together, which we call mu, plus the difference between mean of ith group and the overall mean, that is alpha I, or group specific addition or decrement or increment from mu for the individual group, that is alpha, plus some random error about the mean, whatever, that mu plus alpha I. So Yij minus mu plus alpha I. If you take the first two terms, subtract from Yij, left hand side, what is left as is a random error, that is about the mean mu plus alpha I for an individual observation from the ith group. So in our example, intuitively also come back, FEF will be predicted by an overall mean of overall for all groups, one overall mean FEF plus the effect of each smoking group. In one group it may be smaller, in another group it is further smaller type of things, and plus a random variability within each smoking group. So I hope this model, if you understand, you are able to understand, and if you understand, further things are very straightforward, very simple. I advise you try to think what we are trying to say by this model. Yij is equal to mu plus alpha I plus Eij. Now, hypothesis testing in one-way ANOVA. What is the null hypothesis? You know by this time what is a null hypothesis. The null hypothesis here is the underlying mean FEF in each of the 6 groups is same. As in Ttest, we would have said, if it had been a Ttest, we will say the mean in the 2 groups is similar or same. So it is equivalent to say, if you go back to your model, it is equivalent to say that each alpha I is 0. There is no specific group effect, because whatever, if every group is same, it is same as overall mean. There is no specific group effect. So this is what is null hypothesis translates to. Alpha I is 0. What is then alternative hypothesis? We will say there is at least one mean out of these 6 which is different from the rest. Let me repeat. There is at least one mean out of the 6 group means which is different from the rest. So it is equivalent to say that at least one alpha I is not equal to 0. This is the null hypothesis. Now, conceptualization of ANOVA. Now, again I am going to introduce which are not some terminology which are not very big deal or very difficult to understand. Let ith group mean is simply y bar I. As we were very familiar, any mean is x bar, y bar, such labeling is not very uncommon. So let ith group mean is y bar I. Overall mean for all groups is y double bar. Okay, is that clear? So now deviation of an individual observation from the overall mean, let us take it as our model Yij, not model, based on the model we will extend a deviation of an individual observation from the overall mean. So what I am doing, I am only subtracting Yij minus y double bar is Yij minus y double bar, but what I am doing, I am subtracting one individual group mean once and adding back and then making it as 2 parts. Yij minus y double bar equal to Yij minus y bar I bracket close plus y bar I minus y double bar. So the first term and the last term, fourth term are same, but in between second and third time it is same, but I am subtracting ones and adding ones. So the net result is same. There is no difference from the left hand side. Now, what is this left hand side? Yij minus y bar I. It is the deviation of an individual observation from its group mean. That what we call within the group, what is the variation? Now, what is the second term y bar I minus y double bar? On the right, second term of the right hand side, it is deviation of the group mean from the overall mean. So that refers to what is called between group variability. Okay, so to understand the philosophy of ANOVA, this is an important diagram just to show what is the underlying calculation, what really goes in ANOVA calculations is just this figure. If you understand this, you have understood the entire ANOVA, irrespective of the further specifics and extensions type things, but the philosophy remains same. I have 2 figures here on left hand side and right hand side, both representing 6 groups, each group represented by a straight line, and the dots on each line indicate the individual observations within that group, and the dotted line y double bar, the vertical dotted line, is the overall mean for all the groups put together. So once if you see these, it is pretty apparent that these two groups have different picture of the distribution of the observations within each group. As you can see on the first figure 1, the first line, you have some dots, about 7 dots, which are pretty close to each other. Similarly, for other groups, you can see that the dots may be varying from the overall mean on the left side or right side. That is one aspect which we are not talking about at this stage. What we are talking, within a group, the observations are pretty close. So within a group, the variation is very limited. And if you come to here, the other side, the figure 2, within a group, the observations are scattered more widely. So that there is a variation, within group variation seems to be higher. To make you understand, we are taking an extreme case. The realistic case may be different, but once if you understand this, the number, after you crunch the numbers, the result will be dependent on the overall, at all variations one can think of. But to make you understand, we are taking the simplest case. In the left hand panel or figure 1, you have observations. Within each group, they are very close, as against the other figure 2, where the observations within each group are widely scattered. It tells us that within group variation is very low or small in figure 1 as compared to figure 2. Now, what is between group picture? If you see in figure 1, you can see the first group, the mean seems to be somewhere on the extreme left, and the fifth line seems to be somewhat extreme right. So there are between group variations apparently can be seen because the scatter is limited. All observations, for example, if you take the line 1 in figure 1, are very much towards the left of the overall grand mean indicated by the dotted line, vertical line, as against the fifth or sixth groups which are extreme right. As come to figure 2, you don't have that distinction. You can't say that there is this group is higher, or because the scatter is so much in each group. So now come back to our terminology. So if you say Yij minus Y bar I, that is each individual observation from its group mean or within group variability if you call A, and B if you call the group mean, deviation of group mean from the overall grand mean or between group variability as B. In figure 1, it is very clear B is large compared to within group variability, or between group variation is very large compared to within group variation. But in figure B, within group itself is very large. So between group variability at this stage, it appears that it may not be very large or as relative to within group variability. That's it. Everything is relative. So now we exploit this phenomena for formulation or the calculation of further test statistic. Now, generally speaking, if between group variability is large, between groups there is a large variability, and within group variability is small, as we saw in figure 1, what we say, we tend to reject that all group means cannot be same, or we reject the null hypothesis and declare that the underlying group means are significantly different. Conversely, if between group variation is small and within group variation is large, as we can see in figure 2, the null hypothesis is very much tenable, or we say the null hypothesis is accepted. coming back to the model, Yij minus Y double bar is Yij minus Y bar I as one term plus Y bar I minus Y double bar as another term. So right hand side you have two terms. Now if you take this numerically, this will be absolutely what we say, they are similar. So the difference from left hand side to right hand side is always 0. But to overcome this problem, what we do, we square the both sides. So, and square deviations, then you sum up for every observation, or what we call sum of squared deviations over all observations you obtain, because Yij minus Y bar double bar square whole square, you sum it up because two times, because one on J within group, keeping I fixed for every J, and then after that over groups. So Ij two times you, so it's a double summation. Here also double summation Yij minus Y bar I square plus Y bar I minus Y double bar square. Now you may wonder what happens to like A minus B whole square, what happens to the cross product term. The cross product term will be 0, so it is not an issue. So LHS, what we call the left hand side of double summation Yij minus Y double bar square is what is called total sum of squares for the entire data, and the first term in the right on the right hand side we call it within group sum of squares, and the second term on the right hand side we call between group sum of squares. Now if you have the sum of squares, then you can find what is the, because there are each sum of squares is represented by different numbers, different number of people, different number of groups. So you need to find the what is the mean sum of squares. If there are k groups and total k n observations, between mean square, between group mean sum of squares will be between sum of squares minus k minus 1, because there are k groups, k minus 1. This is the statistical restriction, because if you give the overall mean and you give me, let's come back to our example to make you understand or make you more comfortable. If you give the overall mean and you give me any 5 means, I can tell you the 6th mean. So the 6th group, once if you know the total, only 5 groups are means are independent value, they can take any value. The 6th one has to be, you can always subtract from the overall minus the 5th 5 means, so you can get back to the 6th one. That's how the degrees of freedom becomes k groups minus 1. And within group means sum of squares is within sum of squares divided by n minus k. So this is how you calculate the average sum of squares or mean sum of squares. Now the statistical test will be based on the ratio of between group mean sum of squares to the within group sum of squares. You take the ratio, that will form the statistic, the test criterion for ANOVA. And if this ratio is large, just think of or look at the ratio that I am talking about. What is the numerator? The numerator is between group mean sum of squares divided by within group sum of squares. If this ratio is large, means compared to within sum of squares, average sum of squares, between group average sum of squares is very high. So if this ratio is large, you reject the null hypothesis H naught, and if small, we have no evidence to reject H naught or accept H naught. Or under H naught, this ratio between mean sum of squares divided by within mean sum of squares follows an F distribution with degrees of freedom. F distribution has two parameters. The numerator degrees of freedom is k minus 1 and denominator n minus k. So it follows an F distribution with k minus 1 and n minus k degrees of freedom. This is what all ANOVA is about. Now, from the conceptual formulas, this is what I introduced is the concept that can be translated into actual formulas, numerical formulas. You can derive even from the formulas, you can make it even simpler formulas for between SS and within SS. And so we will not get into these details because they are not very relevant at this stage and for audience like you. Coming back to our example, for FEF example, we have K is 6 groups. K is 6 and total 1050 observations. So N is 1050. And between sum of squares, as I explained, it will be 184.38, and within sum of squares, within group sum of squares is 663.87. But as I told, between sum of squares is dependent on 6 groups, whereas within SS is dependent on 1044 observations. So you have to calculate average. So within mean sum of squares, between mean sum of squares is 184.38 divided by degrees of freedom 5. So it is 6 minus 1 or 5, that is 36.875. And within group mean sum of squares is 663.87 divided by 1050 minus 6 or 1044, it is 0.636. Now what is the ratio test statistic is? Between mean sum of squares divided by within mean sum of squares. So F5 1044 equal to 36.875 divided by 0.636, or F is equal to 58.0. This is the statistic or ratio that you have calculated based on your data. Now you compare it with the tabulated data with an F distribution with 5 and 1044 degrees of freedom. You realize that this 58 can happen if the null hypothesis is correct only in less than 1 in 10,000, or 1 in, here I think it is 1 in 1,000. It could be even much smaller, but for simplicity's sake I just showed it as, in reality it is 0.00001. So I think 6 zeros or so. So it is, what we mean is this 58 cannot happen, or it is unlikely to happen, or it is likely to happen with a very minutest probability if the null hypothesis of equality of the mean FEF in all groups. So the same thing I am trying to explain in detail. F5 1044 is 58, has an associated p-value is less than 0.001. How do you interpret? I am sure you must have understood by this time. P is less than 0.001 implies if our assumption of all 6 FEF means are same is true, then the chance of getting an F value of 58 is less than 1 in 1000. But this probability being very small, and you can have no doubt, or you cannot doubt this probability, what you can only doubt is the null hypothesis. So you may doubt it. So you reject the null hypothesis and conclude that there are at least 2 means significantly different from each other, or there is at least one mean which is different from the rest. Both mean same. So in our example, at this stage, we only know that all means are not same, but which ones are different from which is not yet known. So to make you clear that ANOVA does not tell us which comparison are significantly different. It only tells whether all are same or not. That's all. Okay, so but having said that all are not same, they natural to ask which groups are different then. Which groups are different from which other group? So this question arises only if ANOVA leads to your rejection of null hypothesis, or that we say that is a significant difference among groups. So, but this specific comparison there it can be two types. Once you can specify the groups before the analysis or planning stage itself, you can say my focus is comparison of group 1 versus 3 or group 1, 2 versus 4, like that. If you specify before looking at the actual data, and another option is only after looking at the data, you can do a sort of a fishing or an exploratory manner. You can see which groups are really different from which other group. In the first case, if you have specified that your focus is comparison of A versus C or E versus D, like that, in the first case, what we call a least significant difference LSD procedure is used. And what is this procedure? It is a Ttest only with the pooled estimate of variance or S square in the denominator of usual T is replaced by mean within sum of squares from ANOVA. The numerator, that is T, is y bar 1 minus y bar 2, that is the difference of means. Sorry, there is no bar, I think I missed. Divided by the square root of S square into 1 by N1 plus 1 by N2. It follows T n minus k degrees of freedom. Okay, and under H0, and S square is, this S square is nothing but mean within SS from ANOVA. That is the difference that you should keep in mind if you want to do a pairwise comparison. After ANOVA leads to a significant result, and if the comparison categories have been pre-specified before looking at the actual data. But more often, one goes to compare or group-wise comparisons is after looking at the data, because your inquisitiveness goes up once if you get a significant result. So it is common to expect that to see further analysis which groups are really different from which other groups. So in this case, a large number of potential comparisons are often possible, as we have said. With 10 groups, suppose you have 10 groups, you can have 45 possible pairs of groups to be compared. Now, we said the more tests you do earlier, please recall, earlier we mentioned that the more tests you do, the more probability of finding at least one significant result. So, using a 5% level of significance for each of these 45 possible pairs, testing of possible pairs would imply 0.05 multiplied by 45, or about 2 comparisons are likely to be significant by chance alone. Even if the null hypothesis is correct, you may end up with a significant result in 2 comparisons of the 45. So, to overcome this limitation, or to protect ourselves against this, what we have is a procedure called multiple comparison procedures. And there are different procedures are there, more than 4-5 methods are there at least, for multiple comparison. But the basic idea in all these procedures is to ensure that too many falsely significant difference or false positives in a diagnostic testing, too many false significant differences are not declared. So what do you do? Overall probability of declaring any significant difference between all possible pairs of groups is maintained at some fixed significant level. And this is the philosophy for all procedures, and one of the most common, simplest and widely used method is what is called Bonferroni correction. Bonferroni correction, what we do, we wish to compare 2 specific groups among K groups to test the hypothesis that, let's say you are comparing group 1 versus group 2, and you want to test these 2 groups with respect to group difference or null hypothesis. Alpha 1 is alpha 2 versus alpha 1 is not equal to alpha 2. What we do, the same procedure what we did earlier, compute the pooled estimate of the variance S square or within mean sum of squares from our ANOVA. Now compute the test statistic, which has T n minus k degrees of freedom, y bar 1 minus y bar 2 divided by the same as we have done for pre-specified comparisons. Only difference is for a two-sided level alpha test, you have to have a new alpha. This alpha is not, don't get confused with the group effect. Here we say level of significance, which statistical tests, we fix it before we perform the test as alpha 0.05 or 0.01. So this alpha is not to be confused with the group effect alpha. So okay, for a two-sided level of alpha or statistical significance level alpha, alpha star we define alpha divided by the maximum number of pairs that you are going to test. So then you take a conclusion based on, after arriving at Ttest, based on this new alpha star. For a FEF example, if your original alpha, that is your level of significance, again I request you not to get confused with this alpha with the group effect alpha 1, alpha 2, alpha I, what we mentioned there. This is I am talking, this alpha is 0.05 level of significance that we fix before you perform any statistical test. If the original alpha is 0.05 for the ANOVA, we had to fix, if you have 15 comparisons, alpha star will be 0.05 by 15. That is leads to 0.0033 for multiple comparisons. You perform the test by whatever test statistic as shown above, but don't take alpha p value at 0.05, the upper limit, the alpha, the level of significance at 0.05. Instead, you have to take 0.05 divided by 15 comparisons, because you have all possible if you compare. So your alpha star is 0.003. Now you have all, these are the possible comparisons, all the 15 I have listed here. Non-smoker versus passive smoker, non-smoker versus non-inhaler, non-smoker versus least smoking, or non-smoker versus moderate smoking, non-smoker versus heavy smoking. So if you have these are the, and next is passive versus rest, then non-inhaling versus rest, and like that you have all the combinations. The t value derived is shown here, and the upper limit or all level of significance 0.0033. So all t have 1044 degrees of freedom. Tabulated value at T044 at 0.33%. Usually we take 5%, but with multiple comparisons adjusted for Bonferroni correction, the level of significance is now not 5%, 5% divided by 15, which is 0.33, and the t value, the theoretical tabulated value is 2.94, and any t value above the 2.94 what we got is significant. All comparisons for which t value is more than 2.94 are significant at 5% level, not 0.33, because the original 5 is for the entire test. So for comparisons, for each comparison you divided it by, because 15 comparisons we have divided 5% by 15. But the conclusion is any t value which is 2.94 and above has a significant with a significant at p value 5% level of significance. So now if you see, come back to the actual results, the green ones or star ones are all significant, starred values are all significant. And if you further look at the detailed look at the data, or this analysis reveals, there are basically 3 distinct groups. All the green ones are comparison of non-smoker with the rest. So there is 5 comparison, non-smoker versus the rest 5, all are significant. So that means non-smokers is one specific entity, and Passive smokers are not significant. Any comparison, passive versus non-inhaling and very low smoking category, they are not significant. In other words, passive is as bad as non-inhaling, or passive is as bad as very low level smoking, or the other way, low level smoking is as bad as passive smoking. But if you come to these next two shown in red, passive versus moderate smoking, passive versus heavy smoking, they are significant. So again, these two are different from passive smoking. And non-inhaling versus low smoking is also not significant. Then these are the moderate and heavy smoking are compared to others, all are significant except moderate and heavy. So moderate is as bad as heavy, or heavy is as good as moderate, whatever you want to say. So basically there are three distinct groups. One, non-smokers, it stands separate. Light and passive non-inhaling. Light, passive and non-inhaling is one category, and moderate and heavy smokers are another category. So the 6 groups are really categorized apart from the group-wise comparison of the all possible 15 pairs. We have what I would say categorized that non-smokers are a distinct group which is different from any smoking group, number one. Light, whether it's a light smoking or a passive smoking or non-inhaling smoking, all are barabar or no difference. And moderate and heavy smokers they stand separate. So that's how our analysis followed by multiple comparisons have helped us. So in the example we discussed, the subgroups being compared have been fixed by the design of the study. What we say, it is fixed effects ANOVA. In other instances, you can say each group has as its own mean, but a theoretical average, and there our focus is not comparing the specific groups, but in whether there is an overall difference between groups and what percentages of total variation is attributable to between group versus within group, etc. What we extend this ANOVA to random effects ANOVA. So this is also frequently used in medical laboratory comparisons type things. But the fact, or thus in simple terms, here in random effects ANOVA, we don't presume the group effect is fixed. It can vary depending on the kit, it can type of things, or it depending on the setup, depending on the clinic. So what we say is it has its own distribution. So that is where we use a random effects ANOVA, but the philosophy remains same. We will. And coming back, our FEF example groups are formed by only one variable, that is our smoking status, whether the person is a non-smoker or a heavy smoker or a light smoker. So it is only one dimension. We have formed the dependent variable based on one exposure category or only one factor. So that is why it is called one-way ANOVA. You can have groups defined by more than one group. For the same example, you can extend for the FEF also is whether a sex-wise difference, whether it is a male versus female, or maybe income-wise, maybe residence-wise, maybe literacy-wise. You can go on add. So you can have groups defined by more than one variable, and you would like to look at the effects of each variable after controlling for the effects of other variables. For example, in a study of hypertension and nutrition, blood pressure in three different dietary groups, strictly vegetarian, lacto-vegetarian, normal diet, and 2 gender groups can be analyzed for effect of gender and dietary group. Here in this example, we have 2 variables classifying the outcome. Since we have 2 variables for defining groups as diet and gender, we have two-way ANOVA. Notionally, for any number of dimensions or variables, and we can have n-way ANOVA with n number of grouping variables. But the general concepts and principles remains same as in one-way ANOVA. So more complicated as it involves more than one grouping variable, and there are other methods of analysis also. Instead of ANOVA, you can get into straight away a regression type analysis. So in addition to separate effects of each grouping variable, one can see the interaction between and among grouping variables is also possible. That's another we will not discuss, but I'm just trying to give a hint that what further one can look into this type of. To summarize, to compare means from two independent groups, we use a t-test or student's t-test. But to compare means from more than two groups, ANOVA is used. ANOVA leads to a conclusion that all are same or not. And depending on the conclusion of ANOVA, and if it leads to a significant result, specific comparisons can be made, adjusting for multiple comparisons. And depending on the grouping variables, ANOVA can be one-way or two-way or three-way, etc. So that's it. This is all about ANOVA, and I hope I made clear to you the philosophy of what is ANOVA and what goes inside, what we are really comparing, and when we say there is significant difference, what we mean. Thank you all.